Hello, my name is Amanda Vandenheuvel. This video project is for Professor DeNova's Summer 2020 Physics 1025 online class. This video will demonstrate the physics concept of thermal expansion. Thermal expansion refers to the fractional change in the size of a material in response to a change in temperature. This includes changes in length compared to the original length called linear expansion, changes in area compared to the original area called areal expansion or superficial expansion, and changes in volume compared to the original volume called volumetric expansion or cubical expansion. For most materials over small temperature ranges, these fractional changes are directly proportional to temperature change and have the same sign. This means that materials only or usually expand when heated and contract when cooled. In other words, thermal expansion is the tendency of matter to change its shape, area, and volume in response to a change in temperature. Temperature in physics terms is described as a monotonic function of the average molecular kinetic energy of a substance. With thermal expansion, these changes are larger for liquids than solids because solids tend to retain their shape when not constrained, and therefore are best described by a linear coefficient of thermal expansion, usually represented as alpha. Solids have an area expansion that is almost twice that of their linear expansion, since two perpendicular linear measurements are needed to produce an area, as well as they also have a volumetric expansion that is close to 3 times their linear expansion, since 3 perpendicular linear measurements are used to describe a volume. Opposite of solids, liquids tend to take on the shape of their container and so are best described by a volumetric coefficient of thermal expansion, generally represented by beta. Here, I will demonstrate thermal expansion with 2 different experiments to show how air expands when heat is applied. The first demonstration is the balloon expansion experiment. To start this experiment, I've gathered 2 large bowls, one with boiling water and one with ice water. Then I took an empty glass bottle and I stretched the mouth of a balloon over the top opening of the bottle, making sure that it is airtight. Now you must place the bottle into the ice-cold water for approximately 30 seconds. Once the 30 seconds is over, carefully remove the bottle and place it into the boiled water. Such. Here we get to observe the balloon beginning to inflate. This reaction takes place because the air inside the bottle becomes heated and begins to take up more space and move quicker within the bottle. With this increased speed, the air particles can collide with more force, which allow the particles to have a larger range of motion, which displays as an increase of volume in the balloon. With this experiment, we encounter the density aspect of thermal expansion. Here, density is the relationship between the mass and divided by volume. As the air inside the bottle is heated, it takes up more space but maintains the same amount of mass. With the same amount of air particles in the bottle that are taking up more space, the air becomes less dense. In other words, the same mass divided by a larger volume will make the object less dense. The second demonstration is the balloon and candle experiment. As a follow-up demonstration to the basic balloon expansion experiments we just did. This demonstration is to show how water absorbs heat to prevent the air within the balloon from expanding as shown in the first experiment. For this experiment, start with 2 balloons. One blown up with just air, or a plain balloon, and the other balloon is blown up with air as well, but also partially filled with water that I have colored blue for visibility. And I call this one the water-filled balloon. You also need a candle for this one. So I will go ahead and light the candle. Now hold the plain balloon just above the burning candle. After a short period of time, the balloon will explode abruptly due to the air inside the balloon expanding quickly, and in turn pops the balloon. Next, I take the water-filled balloon and place it above the candle for a period of time. This time, the balloon does not pop because the water absorbs the heat, which prevents the air inside of the balloon from expanding as it did with the first balloon. In this experiment, the water-filled balloon does not burst because the rubber does not reach a temperature sufficient for it to melt or burn. The rubber is stretched thin so that the heat is quickly transferred into the balloon. With the air inside the balloon, this heat is not readily dissipated away from the spot touching the flame. As a result, the first balloon partially melt or burn and then quickly burst. Water, on the other hand, has a great capacity to absorb heat. This is due to the water's specific heat capacity. This heat is readily dissipated into the water and away from the wall of the balloon, so that the rubber does not heat up enough to burn or melt.